figuring out if you had vapor intrusion might seem to be to collect a sample of indoor air and see what's in there. But unfortunately, you will virtually always have background contamination, which is contamination possibly from the outdoor air, but especially from indoor sources. Benzene, toluene, ethyl benzene, those xylenes, those are in 90% of the indoor samples at least. Chlorinated solvents, tetrachloroethene, trichloroethene, very common in background. And you want to know where it's coming from. So you will first collect soil gas, either deep soil gas or maybe subslab, which is right under the floor. And then you know what's in the soil gas, and you will probably restrict your indoor air samples if you have to collect them. If you exceed screening levels of soil gas, you may go to indoor air and you will restrict your analyte list to those things that you found in soil gas. So that's why we like soil gas. It helps us figure out what's coming from where in the indoor air. That may keep us from sampling indoor air. There are numerous indoor sources and contaminants. This is just a short list. Scented candles, cigarettes, glues, adhesives, cleaning products, even modeling clay, lots of things you might not expect. So how do we collect soil gas? Well, we collect soil gas. It's typically broken into two different areas. One is exterior soil gas, deep soil gas used anonymously under a depth of 5 feet. And this is a direct push rig. Geoprobe is a brand name. And they advance the drill rod to a depth of 5 feet or more, connect tubing to the bottom, and then with a pump you withdraw soil gas and can screen it with a meter, and frequently you'd put it into a container and send it off for analysis. It's a good way to collect data fairly quickly. You have to let it equilibrate first, so it might be half an hour per point, but it's cheap. You can collect, relatively cheap, you can collect a lot of data in a short time. The limitation being that in this case, they're temporary points and you can only sample them once. So if you want to go back and resample, then you would probably do something a little more elaborate, perhaps using the same rig. You would use a screen at the bottom of the tubing and surround it with a sand pack and then bentonite going up to the surface. A permanent implant like that is much less likely to leak. A temporary point, a lot of times you have to deal with outdoor air going around and getting into your sample through past the drill rods. So this will give you a permanent implant will give you better quality data at a higher cost and a little more effort. Another approach to getting exterior or deep soil gas is with a well, constructed pretty much the same as a monitor well, with a sand pack, a screen, and grout up to the surface. You can even use an existing monitoring well for groundwater if it's screened right location. You want it to be screened at the top of the water because that's where the vapors are coming from. On the left. On the right, I show where we had installed some dry wells, basically, wells that were set in the vadose zone above groundwater for collecting soil gas. Relatively expensive to install relative to a geoprobe. So that's deep soil gas. Another place you can sample soil gas from is a subslab. And so again, this is the soil gas directly under the floor, under the lowest floor of a building. A very simple approach would be to simply drill a hole through the slab, put a piece of tubing, sample tubing into the hole and surround it with clay of some sort. That's cheap. It won't give you the best quality data. You may not need great quality data if you're only screening. This is something a little more elaborate from the Maryland vapor intrusion guidance. They use the rubber stopper with tubing coming out of it, and they recommend cementing it in. So the cement will take a little more time, but you're still talking a relatively short amount of time to install this and cheap hardware. So that's an advantage, but you probably can't leave that in place with the tubing sticking out and everything. So it's a one-time sample event. You couldn't leave that in an active facility. Something that would allow you to go back and resample is this a little more elaborate point. This figure comes from EPA's Raymark investigation, and it shows up in an awful lot of the guidance, including ITRC. What they did is they drilled a hole through the slab. This is a cross section. Drill a hole through the slab into the soil, and then they assembled. Initially, they used brass hardware store fittings. They assembled. Later, they started putting together swage lock stainless steel fittings, put those into the hole, and then surround them with a cement grout, which is the red on this drawing. And you can get good quality data from them, but the limitation is that getting a good cement seal, as you see somebody doing with a syringe here, getting a good seal in between the slab and the hardware can be very difficult, can be very time consuming. And you don't want to have any leaks. You also have to install it, come back the next day after the cement sets up before you collect your sample. And it's not unusual for the cement to break, then you've got to re-cement it, come back the following day. So leakage and breakage is a big issue with these. There's another issue in that you can repeat sampling at a point any number of times, but you cannot remove that hardware and take it to another point. If you're using swage lock fittings, the costs will add up somewhat. So those are the limitations with this. For which reason we invented the vapor pen. The vapor pen is a single piece of metal, at least the original vapor pen is, brass or stainless. Instead of using cement to hold it in the slab, we put a silicone sleeve around the base. So you drill your hole, dust it out with a bottle brush, and then you hammer it in. The actual installation takes maybe 20 seconds. There's no cement to fiddle with. And depending, you may want to let the hole equilibrate before you sample. But if you're looking for pressures or other kind of data, you could get your readings immediately. It has a barb at the top, a 1/4-inch barb fitting for the sampling. And in the middle is a threaded section. You use a threaded section to screw on your installation removal tool to take it out whenever you're done sampling. You can also use it to screw a cap on to cover it up. Next. So here we are drilling a 5/8 inch hole for an installation. I show two configurations here. You can use a stick-up configuration. We do that on the left there. We do that a lot when we're looking for sources. We may drill a number of holes in a grid configuration, trying to find contamination under the floor. We'll drill a 5/8 inch hole, dust it out, hammer it in, and a little over an inch of vapor stick up above the floor. So you put a traffic cone over it, come back and sample it later in the day, remove it at the end of the day and fill the hole. If you're going to do repeat sampling, which is more typical of vapor intrusion, then you drill an 1.5 inch hole to a depth of 1.5 inches. Then you drill a 5/8 inch hole through that and install a vapor pen in that. And then the entire vapor pen, barb and all, will be below grade. You can walk over it without tripping. You can run a forklift over it. I do want to point out, I have this reminder for myself, vapor pens in any subslab device by definition is for slab use only. Occasionally people have asked us if they can put this in the middle of the field, of a field of grass or whatever. The answer is no. It's designed to go into concrete. We've had some success in asphalt as well, but you can't put it in the middle of soil. Next. So here are some of the accessories for the vapor pen. You see in the lower left, a flush mount installation just after it was installed. And a minute later on the lower right, we have a secure cover, the stainless steel cover over it. You can also use a cheaper plastic cover if you like. The drill guide there on the upper right helps you drill the first hole, the bigger hole, to the proper depth. And then you put it in the hole and you drill a 5/8 inch hole through the middle of it. That way your smaller and your larger hole are on the same center. One is not off a little bit. Makes it a lot easier to work with. Some other accessories, some people like to put a filter on the bottom of the vapor pen, so you can screw that on. There in the upper left is a filter. Some people feel that there's an issue with the fact that the vapor pen only goes a little more than an inch into the slab, and the slab may be 6 inches thick. So if you want to avoid exposure between soil gas and the bottom 5 inches of the slab, then you can put either of a couple of fittings on the underside of the vapor pen and extend it down to the depth of the base of the slab. And then that sieve there you could put on the bottom of the barb extension so that you're not poking soil into the extension when you install a vapor pen. This is the latest generation of vapor pen and vapor pen accessories called the Flex VP. We've had them only for about 2 months. Some people don't like barbed fittings for various reasons. It comes equipped with a barbed fitting there on the left, but after you install it, you can unscrew the barb fitting and put a swage lock compression fitting on top of it if you like. And then you'll have the exact same hardware in between from the vapor pin that you would have at the Sumacan on the other end. So you're going swage lock to swage lock if you like compression fittings over barbs. Another device that you can put in the top of the vapor pin is this quick connect made for us by NTech. And this goes to NTech hardware, which just more or less snaps in place with no accessory tubing. And again, no accessory tubing, it can go directly to bottle vacs, certain containers, etc. So the pros and cons of vapor pins, they're very quick to install, unlikely to fail. I've put in many hundreds of them. I've never had a failure. And the only few I've heard of were where they had broken up concrete. They're reusable. As I mentioned, you can take these out, decontaminate them, use them at another location. You can resample the cemented endpoints, but you can't move them, take them out and move them somewhere else. So while the vapor pin initial cost may be somewhat higher than compression fittings set in cement, second time you break even, and the third and the fourth and the fifth time, it's basically free. I've used mine an average of 7 or 8 times a piece. I've never damaged a single one. So, and of course you're saving time on the installation because they go in so quickly. So once you've installed your subslab sample point or other outdoor sample location, and you let it equilibrate, then you want to purge the tubing so you can get soil gas in there in place of indoor or outdoor air. A simple approach to that is a syringe shown on the left. A syringe will give you a good control over the purge volume. The rate isn't necessarily constant. You can purge with a peristaltic pump. It's a little harder to control the volume and rate of purging, but it is convenient for a lot of people because about anybody in environmental sampling probably already has a peristaltic pump. What I like to use on the right there is a multi-gas meter. This is basically the same meter you'd use to enter a confined space. It has a PID added to it. The nice thing about it is, besides the fact it purges at a controlled rate, in this case 200 milliliters a minute, I'm getting data as I'm purging. And the ones that I really want to focus on are oxygen. The oxygen virtually always drops, and the amount of oxygen is very critical to vapor intrusion, especially if you're working petroleum sites. If you have VOCs, you'll see the VOCs rise. And that data, again, is very critical because you may install a lot of points and only screen them here and there, or screen them everywhere, but then only collect your samples for analysis at the couple of hot spots. So you don't have to send a whole lot of points in for analysis. You can screen them for next to nothing. Here are just some other meters. There's another multi-gas meter on the left, a low-level PID in the middle, and a more or less conventional PID on the right. Now, one of the issues with soil gas sampling is that there can be a lot of hardware hooked together, and there's a tendency for leakage. There's also a tendency for leakage of subslab sampling points, especially in my experience and most people's experience, I think, is when you have the cemented endpoints. They tend to break loose, etc. So you want to make sure that when you're collecting soil gas, you're actually getting soil gas and not indoor or outdoor air. So you test for leakage. This is one approach, using a tracer gas. Helium is a preferred tracer gas in most cases. What they did here, they put a so-called shroud. You might use a plastic bag, but they used a stainless steel dome. You put a stainless steel dome over the sample point. They introduce helium in at the top, that's your tracer gas, and then you sample the soil gas, or you test the soil gas with a helium detector. And if it shows more than 1 or 5%, whatever your DQO, shows more than a little bit of leakage, shows more than a little helium, then you have to tighten up and somehow fix your leak. And it's a technically elegant approach in my mind, but the practicality is a bit wanting. This is a picture from an EPA guidance document, the same guy who made that figure for the cemented endpoint. He had problems with leakage, so he decided helium was the way to go. And again, I think it's technically elegant, maybe, but there's a lot of hardware associated with this, and there are a lot of problems. For one thing, it can be difficult to get lab-grade helium. Stuff you use to fill balloons can be impure. Also, if you're at a petroleum or other site, a landfill site that has methane in it, methane will give you a false positive on many or most helium detectors, and you'll think you have a leak when you don't. As much as anything, my biggest complaint about helium is that it's cumbersome and bulky. And your biggest enemy, as I'll discuss in a little bit, is spatial heterogeneity. Soil gas is very variable. It's highly variable over distances, over short distances. And you need to collect multiple points. And this apparatus will not make that easy. Another approach to leak testing are liquid tracers. You take isopropyl, or maybe isopropyl, say you put it on a rag, and you put that at the base of your tube into a slab. And in a couple of weeks, when you get your sample back from the lab, your analysis back from the lab, if you had isopropyl in your sample, you know it was leaking. Unfortunately, it's too late to do anything to fix it. And shaving cream, same idea. You heap that up around the base of the tubing. It's cheap, it's simple, but you don't know about your leak until it's too late. And if you have elevated levels, then you can ruin your sample. And if you do have a leak, you'll generally always see it in experiences I've seen, because a certain amount of it permeates a tubing, and you'll know that you had some of your leak compound getting in, but you don't really know what percentage of leakage that represents. So what I like to do, I've been doing for some years, is mechanical leak testing. Just in a word, we have an SOP on our website that describes that, but you impose a vacuum on your sample train, and you can see the vacuum gauge there on the right. If it holds a vacuum for several minutes, then it isn't leaking. It's the same as a shut-in test on a SumaCan. The other thing I do is you test the vapor pin itself by surrounding it with water. There's a PVC pipe held to the floor with clay. Pour in distilled water, and then you do your purge. If water doesn't go down the hole, and I've never had that on a vapor pin, then it wasn't leaking. This is much simpler, much cheaper than any other leak testing. If you have a good subslab point, you won't have any loss of sample. So-called water dam. So. Okay, I'm going to talk a little about sample containers. See, I passed one. I need to go back. Yeah, there. This one looks the same picture as the previous one. Sorry. So here's a SumaCan, conventional SumaCan. They're more or less been regarded as a gold standard for analytical samples. They work well. They don't need a pump. They're evacuated. They can give a good data quality, but they're bulky. You have to pay to rent them. They have to be cleaned, and if they're not cleaned properly, you might see cross-contamination from the previous sampling event. And they tend to leak and other kinds of things because they're mechanically complex. A simpler and less costly approach is a glass container. Bottle back on the right, some other glass files there below. Bottles, because they're disposable, won't show cross-contamination from previous sampling events. They're cheap, they're relatively compact, so they're a little easier to ship in many cases, especially those lower ones. But you're limited to grab samples. You can't time it over 8 hours, 24 hours as you might assume it can. You'll have typically a higher reporting level because you have a smaller sample size. And there aren't as many labs can run these things. They take different apparatus for the lab than you would use for a SumaCan. So not everyone runs these. Okay, so that whole air that I was describing there, now I'll talk about air samples via sorbents. In this case, you absorb the contamination onto the sorbent and you send it to the lab without any air. So it's very compact. That TO17 tube in the lower left is about half the length of a pencil. So that's an advantage. You can get very low reporting levels. You're not limited to a 1 or a 6 liter canister. You can pull 100 liters of air through a TO17 tube if you want to and analyze 100 liters of air. So by doing that, you can get very low reporting levels, and you can look at some of the heavier compounds, some of the SVOCs that wouldn't show up in a SumaCan. So those are advantages. Drawbacks of the sorbent tubes is that different sorbents they behave differently around different compounds. You might have one sorbent appropriate for vinyl chloride and another sorbent appropriate for tetrachloroethane, PCE. And if you're doing both, you might have a little bit of trouble finding a sorbent that'll do both. You need to have an understanding of what compounds you have and what their concentrations are before you sample, or you'll get unusable results. Also, they're not analyzed by as many laboratories, at least here, as whole air samples from SumaCans. Passive sorbents, I forgot to mention, but that's okay, you don't have to go back. The active sorbents, you're going to need some kind of a pump. You have to make sure the battery keeps working, so that's maybe a limitation. But you have to have a controlled flow rate. You'll want to know exactly how many liters of air you pulled into that sample. Passive sorbent is simpler. It doesn't have any pump. You just hang it up for indoor air, or maybe you bury it to collect soil gas. And so it's much simpler to use. And again, it's good for heavy compounds, good for low concentrations if you leave it there longer. But again, the sorbent is compound specific. You have to match the sorbent to the compound, and you don't get air concentrations. That's a serious limitation. You'll know how much contamination you had, and you'll know that this compound is higher concentration than that compound perhaps, but you won't know how many liters of air that corresponds to. You won't have a microgram per cubic meter volume. You can kind of calculate it, but you won't know exactly. All right, temporal and spatial variation. That's variation in concentrations over time and variation concentration over space. EPA said in one of their studies that temporal variation in indoor air was a factor of 20 or greater. And that's pretty close to what I've seen, 10, 20-fold change in indoor air in the concentration. Soil gas changes much less. It's not surprising because every time you open a door, every time you spray something from an aerosol can, your indoor air concentrations are changing. But soil gas moves much more slowly, so your concentrations are much more stable. They said in the subslab soil gas, they saw a variation of a factor of 2 or less, which is in line with what I've seen in a lot of soil gas that I've collected. Subslab, on the other hand, those soil gas concentrations generally vary a lot over space. Indoor air typically is not very different in one part of the building than another, maybe a factor of 2 or 3 in my experience. Soil gas can vary by factors of 100 or 1,000 over just maybe 20 feet. So how do you address that? Well, here's an example of temporal variation from EPA's guidance. Again, the same study, they show the temporal variation in indoor air at the top and in soil gas at the bottom. They don't look that different, but if you look at the scale, your indoor air is on a logarithmic scale and your soil gas is on a linear scale. The indoor air is changing by a factor of 20 or more. The soil gas is changing by 20 or 30%. So how do you deal with temporal variation? One way is to have multiple sampling events and figure that if you collect multiple times, the guidance often says 3 times or more, then you'll be sure you catch it at its highest or close to its highest. Get a representative sample. You can also collect a sample over a longer duration. If you have some way to sample over the course of a week or a month, then you'll know what's representative for that time period. Now, there is a limitation, though, because you can't use every sample type for different sample durations. You can't, for example, use a bottle vac for a 1 week or even a 1 hour sample, probably. It's usually only a few minutes. And you wouldn't necessarily be able to use a sorbent sample to get something very quickly, maybe if you used a syringe. Now, I didn't show a picture, but another approach is you could have a real-time electronic device that gives you readings of your concentrations every minute, and you can leave it parked there for days or weeks. But they cost tens of thousands of dollars, so it's not an economical approach. You deal with spatial variation by simply collecting more samples, or at least collecting more screening values and then sampling where you see something hot. This is a picture of a building where we conducted our first gas survey using the vapor pen about 5 years ago. And we had just 2 guys and a hammer drill going out, installing 30 points a night, letting them equilibrate for a couple of hours, sample, pull a vapor pin, plug the hole. And just did that, and over the course of a week, we sampled 140 plus points. The circles here show PCE in blue, TCE in red, dichloroethene in yellow, and those are on a logarithmic scale. Those are really significant differences in between them. But we were looking for a source. And what we find very often is my magenta rectangles there in the lower part of the picture on the east, actually, and another magenta rectangle on the inside is those were suspected sources. Those were decreasing pits and storage tanks. And we figured we'd find the contamination at those locations. We didn't. We found them somewhere else different entirely. And what we found then, and we found repeatedly since, when you do a soil gas survey, you'll find that the contamination more often corresponds to where the back door was in 1950, because people disposed of solvents very differently then than they do now. And nobody even remembers that. 1950, I wasn't even born yet, and nobody's going to remember how that got there. So we figured this out on the basis of aerial photos, et cetera. Figured out, yeah, that used to be the back door, but you wouldn't know to look there probably. And so you need to collect a lot of samples. This is a graph showing a transect across that same location. That little black line on the left is my transect. My sample spacing was 20 feet between points. And you can see my soil gas there in the PCE graph, which is blue. I'm about 100 in the first sample on the left. I'm about 100 again on the second sample, 100 or a little over 100 on the third sample. Then abruptly 20 feet later, laterally 20 feet, I jump up to 12,000. 20 feet over from there, it goes up to 38,000. And another 20 feet farther east, it jumps back down close to zero. That's a lot of variation. And the only thing you can do is to collect a lot of screening values and then probably send some of them off to the lab. But that's the only way to whip spatial variation. So, soil gas, the advantages of soil gas as a sampling technique. It's very useful to locate and delineate sources of contamination, sea contamination, and a couple of others. It's less vulnerable to background in indoor air. If you go into indoor air directly, you're going to see benzene, toluene, and lots of other stuff. Soil gas will tell you what's potentially coming from vapor intrusion. Soil gas is closer to receptors in groundwater. Groundwater is useful as a first step in vapor intrusion, but it's far enough away from the receptor, from the building, that you don't really have it won't give you a very good estimate of what's going on in the indoor air. You'll get a lot closer by collecting soil gas, especially sub-slab soil gas, which is the last thing soil gas does before it enters a building. While I talked about soil gas being heterogeneous, it is, but it's a lot less heterogeneous than soil. We've used subslab soil gas to locate contaminated soil under buildings. In this case, we didn't care about vapor intrusion. Case not too far from this other site, and the same number of points, 144. We had a building soon to be abandoned, but we realized it was cheaper to install a bunch of vapor pins, screen them, send a couple of them into the lab. We could find soil contamination that way a lot easier and more accurately than trying to collect 100 soil samples. And you can read soil gas data with field instruments. It's very hard to get a VOC reading off of groundwater or soil with a real-time instrument, a field instrument, but with just a basic PID and soil gas, you can find out an awful lot about the location of contamination. So that's why we like soil gas. Any comments or questions?
Thank you, Mort. That was fantastic. Yeah, any question or type it in to the chat box. I just thought I might start off with one, if that's all right. What was the procedure for decontaminating the vapor pins between installations?
When we first get vapor pins from the manufacturer, they have cutting oils and that kind of thing on them. So we put them in a sonic. And we have one liquid we use for brass and another for stainless steel. But basically, you could scrub them up with a good lab grade Alkanox or other detergent. And then you put them in an oven. Is it 100 degrees centigrade? 130 degrees centigrade. We put them in there for, I think it's 30 minutes. And it's the same thing, basically, that cooking process is the same thing they do with Suma cans.
Yep, makes sense. Thank you. So we have a question from Dale. Can you see that one there, Mort?
Soil gas, I don't see enough variation in soil gas to really have seen that much of a trend. Indoor air may be worse, but I don't see much of a trend in soil gas changing over time. Yeah, well, I don't see that much difference between winter. I'm not sure I've seen a systematic trend.
And in indoor?
Indoor. Um, I don't even know if I'm not even sure that I see it in indoor air because at least where we are, we're running the air in the winter for heat and we're running it in the summer for air conditioning. I'm not sure they're all that different. There's a debate when what actually happens. As a rule of thumb, they say when you run your heating system, you're drawing in soil gas, but you're also drawing in more outdoor air. So some people make the argument it could go the other direction. I think you just have to sample multiple times to know.
Yeah, so I suppose that it must be like a lot of different systems where over time you start getting a sort of a feel for variability with different maybe building types or different soil types where there's a bit of a trend in overall standard error.
Did you catch that question, Mort?
That's the last one. No.
Alistair, can you ask that again, please?
Yeah, I just thought it might be one of those things where over time you develop sort of a rough feel for variability in different regions, so different geographic regions, different times of year, different soil types.
Very possibly. I've worked outside of Ohio, but I don't have enough. I don't have multiple sampling events in everywhere. The only multiple sampling events I've done are in Ohio, so I would be hard pressed to compare uh, temporal variability for other states. We have sampled in other parts of the country, usually to locate sources or just to find out if they have a problem. But then the follow-up sampling is usually done by the other consultants who ask us to help them with it.
Okay. If anyone else has a
I
question,
will mention.
oh, sorry, go on.
Well, I did want to say one thing with temporal variation to keep in mind too is since soil gas doesn't vary a lot, if you're 10, since you don't have a factor of 10 variation in soil gas, it's only usually 2 or 3. If you're 10 times below screening level, it's pretty easy to make the case that you don't need a sample indoor air. Sometimes agencies are afraid that well temporal variation, you don't really know that you may have to sample multiple times your soil gas, but you can make the argument that I might get temporal variation, but typically only a factor of 2 or 3. So if I'm 10 times lower than screening level, there's no reason to ever sample soil gas a second time.
Mm-hmm. If anyone else has any questions, please type them in. Otherwise, I'll ask one for my own benefit, actually. You're saying that oxygen readings were important for, I think it was petroleum contaminated sites. I was just wondering if you
Yes,
could
very
elaborate
much
on
so.
that.
Well, I like using the oxygen data in two ways. You don't always see the PID rise if you don't have a high level soil gas. And so it helps me know when I'm done purging, usually about a half a minute with a vapor pen and a 6-inch slab with the meter I'm using. But I watch the oxygen nearly always drops, at least a few percent. So I watch the oxygen level drop, and when it levels off, then I feel it's appropriate to purge. Some people may prefer to calculate the purge volume, but I like to wait until my concentration stabilize. And oxygen nearly always drops, even if you don't have vapor, so that's useful. But also it's useful in a couple of ways. It's a qualitative indication if you have a leak. If you have near normal oxygen, 20.9%, then you might want to check to see if you have a leak. And you also will typically find more oxygen around the exterior of a building, but we often map out the oxygen and you can find channels and structures under the building on the basis of where you have high oxygen levels. Sometimes piping or other kinds of things will cause you to have high oxygen in the interior of the building. So it's useful for that. In terms of petroleum hydrocarbons, and this is discussed a lot in the ITRC petroleum guidance and in the EPA petroleum guidance from 2015. The hydrocarbons, not so much chlorinated, but because hydrocarbons break down more readily, they use up a lot of oxygen. In fact, if you have a lot of hydrocarbons or if you have a large floor for other reasons, have a hard time getting oxygen in fast enough, your oxygen levels can really plummet. And that tells you you may have trouble getting natural breakdown. So you typically measure oxygen at a petroleum site, and you may even do depth profiles to figure out if you have natural degradation of your petroleum. Um, So you also, low oxygen is associated with methanogenesis. You'll get methane generation when you're typically under about 4% oxygen. So those are all good things to know. A lot of times you'll see oxygen below 4% and your lower explosive limit, your LEL, then will rise on your meter. So those are good things to keep track of.
Excellent, thank you, Mort. We also have a question from Richard here. I'll just give you your microphone here, Richard. You should be getting voice at some point. Otherwise, you can tap your question in as well.
Yeah, I'm not hearing it.
Yeah, just still sending in voice at the moment. I was just typing it in now. Get those two fingers going a bit quicker. Oh, there you are.
Can you hear me?
Yep, loud and clear.
Good, I'll stop typing then. Okay,
We can hear you.
so thank you for this. It's very good. We measure the concentrations of the vapor beneath the slab, and then there's this leap of faith that there's a certain potential for that gas to get into the indoor air. In the past, we used to use a publication that had studied fractures in concrete and come up with some numbers for ability for gases to go through those fractures. I was just wondering, has the industry come up with an alternative approach to that, or how do you then, where you have high concentrations in the subsurface slab, actually extrapolate that to a true indoor risk?
Yeah, that's attenuation factors. I had it on the first or second slide. I didn't talk about it in depth, but there have been a number of studies where they compare subslab soil gas or deep soil gas or groundwater for that matter to indoor air concentrations. US EPA uses an attenuation factor, default attenuation factor for soil gas of 0.03. So they assume that if you have 100 micrograms per liter of PCE in the soil gas, that you'll have 3.03 times 100. You'll have 3 in the indoor air. Now that's extremely conservative, and that's not based on their median value. They deliberately make it safe. They deliberately make it overly safe, I guess. They find, in fact, in their study, they found only really 0.3%, 0.003 times your soil gas concentration is representative of indoor air. But in fact, what we found is much, much lower whenever I can. And you're not always able to, because people don't always want you measuring indoor air. But when I can, I always collect soil gas, subslab soil gas, and indoor air concurrently. And we found that the attenuation, that is the ratio of soil gas to indoor air, is usually closer to on the order of 1,000 to 300,000 to 1. You don't get anywhere near 3% soil gas in indoor air as the default attenuation factor would suggest. It's usually much, much less. And models will show you that. But we're also dealing in commercial industrial settings, which have a higher air exchange rate than EPA was using in their residential models. That's part of the difference.
Okay.
Any other questions while you've got a voice here, Richard?
I think so. In terms of when you do these assessments, the actual physical inspection of the concrete slab itself, I presume, forms part of your assessment process.
Right.
You typically take photographs and that sort of thing to get that you would report against, or is there some kind of, I guess it's such a critical factor in it all, is there a protocol for like mapping fractures of slabs or reporting on condition of slabs as part of it?
I only report on it. I don't necessarily photograph it, and the facilities I've been in typically haven't had major problems. they may have knockouts in the wall. I see that more commonly, where they'll run a pipe through a block wall, and then depending, the vapors may be able to come up into the block wall and get out there. You may have gaps around plumbing. That's a common place for vapors to come up through the floor. Large cracks, I've sometimes measured soil gas coming up from a crack, but usually there isn't much to photograph. But if it's excessively cracked, you'd want to comment on that.
Okay. Thank you very much.
Thanks, Richard. Yeah, I think David's just typing a question there as well. And there's also a question there from Dale Mort as well, if you can read that one.
Right.
Mort, I'll read it. It says,
particular.
yeah, do you see mud TCE in particular or with chlorinated salts that vapor plumes are moving against normal groundwater gradients? For example, vapor associated with a DNAPL in groundwater.
We haven't worked at a lot of DNAPL sites with chlorinated solvents, fortunately, but we see a lot of TCE in indoor air. And TCE, as you may know from the EPA's background report, shows up in residences 40% of the time, even when there's no vapor intrusion. So you shouldn't be surprised to see a lot of TCE in indoor air. And when we do collect subslab and indoor air, we frequently find consistent ratios. So we know that it can be getting in through vapor intrusion. So yeah, we do see it. It does show up, and it can show up above screening levels, because at least in the US, screening levels are very low. For residents, 2.1 micrograms per liter. It's not very much. It's very easy to get found from background and certainly from vapor intrusion. Do we take into account subsurface structures such as conduits, backfilled trenches during assessment? They may impact accumulation of soil vapor. Yeah, I mean, you're talking basically preferential pathways. We do if you have a large large sewer system or something like that, a tunnel impacting a building, and we see that a lot in commercial industrial buildings, tunnels coming into the building. Yeah, you'd want to comment on that. That can be a preferential pathway. Ordinary plumbing typically is not, but yeah, that can be.
What about GPR survey? That's the next question.
Well, we do GPR surveys, and usually before installing vapor pins, we'll do them, so we'll have an idea on that. To do a GPR survey looking for conduits and tunnels, no, I don't think we haven't done that so much. Usually we'll know enough about the building to have some idea, but not always. You could do that, might be useful.
I think your example about the doorway in the 1950s is a good example why the National Environment Protection Measures over here, one of the first things they say to do is detailed site inspection and history as possible to help guide your sampling.
I think along with that detailed pictures that you would take would be exactly that spatial 20-foot spacing that Mort was talking about to get yourself more data points in order to get a better picture of the site that you want right along with all your pictures, that kind of stuff.
Well, in fact, I should have mentioned, brought up the issue of photographs. A lot of our sites, a lot of the clients have confidential manufacturing procedures. They may not like you taking pictures. So sometimes you can't.
Right, hence the reason for more data points.
Okay. Excellent. Thank you, Mort. Thank you, Laurie, and thank you, Craig. That was absolutely fantastic, extremely informative. And the audio was incredibly clear. That was fantastic. So thank you for everyone for attending today's session. I'll be sending through details that will allow you to access our online training portal, which has some associated material based on today's session, including a brief summary of the NEPM for assessment of site contamination here in Australia, including some of the jurisdictional differences between the states. There'll be a recording of this webinar, as well as some more detail on the equipment that Mort talked about, including vapor pins and also some continuous monitoring options as well. as well as some detail on some other courses that we have in assessment of site contamination and a lot of other environmental monitoring applications. There's some more information on those there as well. We'll be doing a series of these webinars going forward as regularly as possible, so it'll be fantastic to have you all on board for future ones as well, but we'll make sure you're all kept in the loop. So finally, thanks again, Laurie, Morton, and Craig. That was absolutely fantastic.
Okay, thank you.
Thank you very much.
Thanks.
Thank you. Speak to you soon.